Okay, we're going to talk about two things that deal with waves, primarily sound waves, but it's not the only type of wave that this deals with. And the first is the concept of beating. Remember, waves interfere. They can add up together to make something bigger, but they can also cancel each other out and make something smaller. It can go either constructive or destructive. So if I have two waves, one that looks like that and one that looks like that, they don't match up exactly. So what's going to happen is I'm going to get something that looks like this when I put them together. What this is this is called a beat. A beat is going to be an up and down sound due to constructive and destructive interference. This would be constructive interference. Right here would be destructive interference. So it's going to add up to something that happens like that. So for example, if I had 440 hertz tuning fork and I had a 442 hertz tuning fork, they're out of tune. They're slightly different frequencies. Here there's a difference of 2 hertz. So what I'm going to hear is 2 constructive interferences per second. So the beat frequency is 2. If I had 444 hertz, it also has a difference of 2. So the beat frequency is still going to be 2 beats per second. So this is the up and down sound. This is primarily used in tuning instruments. What they do is they set either an electronic tuner or a tuning fork to a certain frequency, and then they adjust the string for a stringed instrument until it matches it and does away with this, and you get a solid loud tone. Now let's take a look at a couple examples of this and take a look at the math that goes with this to hopefully understand this. Let's say I have a 256 hertz tuning fork, and what I get is a beat frequency of 2 hertz. What is the other tuning fork? So this is my given. This is the one I'm looking for. Well, if I have a beat frequency of 2 hertz, what that means is I can be 2 up below, which would be 254 hertz, or I can have 258 hertz, which is 2 above. Can't have anything outside of that. I don't know which one of those it is. That's why trained musicians have really good ears. They can tell that things. I can't. Now let's say what if I had a 480 hertz tuning fork and I was getting 6 beats in 2 seconds? What would I have then? Well, if I had a 480 hertz, first of all I need to figure out the beat frequency. Well, 3 beats for every 2 seconds. How about 6 beats for every 2 seconds, which is 3 hertz. So therefore what I have is 477 or 483. It can be either high or low. I don't know which one it is. It can be one of the two. By the way, if it's high, it's sharp. If it's low, it's flat. But that's up to people that have really good ears. Now, let's talk natural frequency. Everything has a natural frequency, especially if it's homogeneous and it's all composed of the same material. So if I drop something, if I drop a baseball bat, if I drop a metal screwdriver, you're going to hear a different sound because they vibrate at a different natural frequency. The natural frequency is the frequency at which something's naturally going to want to oscillate at it or vibrate at. We see this a lot with musical instruments. For example, piano, 88 strings. Each string has its own unique natural frequency. And what you do is you pluck different strings, and that's how they work. Cellos, guitars, things like that, you change the length of the string. So you can change the frequency based on where you attach it at. So woodwinds, you lengthen or shorten the string. So you have multiples. You have many different natural frequencies of that string. Now, I can only get certain frequencies off each string. That's why they have 6 strings, or in some case 12 strings, stuff like that. For any type of air thing, it's related to the column of air. And valves and all that stuff change that. So that's kind of important with that. So natural frequency is something we take advantage of a lot with that. Now, we have seen some disastrous side effects of this. Oh, well, I guess let's go to the next thing. If you force something to vibrate, if you force to vibrate at the natural frequency, what's going to happen is the motion is going to get larger and larger and larger. A couple places we see this, a swing set. As a kid, you're swinging on a swing set. You add a little bit of vibration at the correct time, your overall vibration can get bigger, but it has to be in with the natural frequency of it. This is something called a resonance. Resonance quite literally comes from the word resounding. We'll do multiple demonstrations of this in class, but resonance is when you force something to vibrate at its natural frequency and you add some type of vibration. Probably the most dangerous and destructive one of all time is the Tacoma Narrows Bridge. In 1940, bridge came down due to aerodynamic effects on the bridge, which caused it to resonate at the natural frequency of that bridge. Another place we see it is opera singers and wine glasses, and you can Google that if you want. Another common way you might do it is to wet your finger and run it around the lip of a wine glass that looks like that. It's got to be a good wine glass. Take and wet your finger, and then rub your finger around the glass in circles, and you will cause a wave in here to resonate. Also, when you take something like when you pluck a guitar string, what you're causing is the entire front of the guitar to vibrate at the same frequency as the guitar string, which causes the air inside the guitar to vibrate at that same frequency, which helps multiply the sound. Electric guitars work a little bit different and stuff like that. Well, we'll talk more about this stuff in class, but I want you to understand what beats and resonance are, so we can continue our discussion of waves.